It probably wasn't that much.
Hello. Today I'm going to be talking about image models for the capstone technical presentation. Specifically, I'm going to be focusing on CNNs because these are of direct relevance in our capstone project. So sort of the fundamental question that we want to ask is, how do we train a computer to recognize features of an image? So what is a feature? For example, let's say I give you an image of some space. Maybe the picture might contain a table in it, and I want, an algorithm. I want to be able to train my write a computer program that I give it this picture, and it'll tell me with some very high accuracy whether or not there's a table in it. Okay, and maybe it's not just a table. Maybe there's a mountain. I want it to tell me whether there's a mountain. I send it a picture. How much fog is there? And so you can sort of create various image recognition, image processing, sort of computer vision kind of tasks like this. And I'll talk a little bit about why I chose the topic, which is that our project features hard computer vision problems. In particular, since we're developing an adaptive learning platform for children with autism spectrum disorder, we will need sort of, one of the things that we have is that we want our platform to be able to look at the video of the people who are using the platform and to sort of detect the emotion that they're feeling based on sort of the facial expression that they're making. And this is a computer vision problem. This is pretty difficult. You need to look at it. Firstly, you need to know that there is a human face in the frame. Secondly, you need to be able to look at this human face and determine what is the emotion that it is making. Further, we want this to respond in real time as the student uses the platform. Maybe if they're feeling sad or if they're feeling frustrated, the thing should become a little easier. And if they're sort of feeling very happy, or if they seem kind of bored, the thing should become more difficult. And it should adaptively challenge them based on that. So it's definitely a difficult problem. The state of the art at the moment, there's lots and lots of models that are used for sort of these kinds of computer vision problems. The architecture that we will probably be able to use is a convolutional neural network, which is a variant of deep nets. So basically, this is a neural network where the layers are permutation equivariant in the sense of if you take Sn as a group action on these layers, and they're equivariant under this. This is going to be a permutation equivariant deep net, right? Or okay, I guess permutation is not really relevant. It's just some group, but okay. And so there's sort of a refinement of this idea. The C stands for convolution, which is sort of an operation that's basically if I give you two power series and you multiply them together, this is a convolution. But if I give you two polynomials and you multiply them together ternwise, if you look at the polynomial as an array of values, this is also a convolution, right? So this is sort of the idea, is that you have this sort of kernel which is small, and you convolve it with this image repeatedly, and the image is big, and this sort of will expose some information about the image, and you pass this stuff to the next layer, which will have another kernel which you convolve, and you sort of keep doing this. And you refine the image in such a way that you can run something which is much less, the end basically of this convolving chain will tell you something like where are the edges of the objects or something like that. So the relevance to our project, of course, is that we need to take video of the faces of people, and we need to interpret their emotions. And this is just a vision task. This task is just a computer vision task. And so the approach that that is plausible is to use a convolutional neural network. These CNNs can have some diverse uses as well. They're not just something that's only useful in computer vision. There are applications in audio processing, because convolution is sort of fundamentally related to the Fourier transform, in the sense that if I give you maybe two vectors, the pairwise multiplication of these vectors in sort of time space is equivalent to convolution in frequency space, and the opposite also holds. So if you want to compute a convolution, the fastest way to do it is to do a Fourier transform in n log n with FFT, and then just do a pointwise multiplication, and then take the inverse again, which is n log n because of FFT. And also because of this sort of relation to the Fourier transform and to computing things in frequency space, there are implications of CNN also to natural language processing, because they can detect patterns that are not that easy to see. So CNNs are a simple and versatile method of detecting sort of features in data that can be kind of difficult to see. And they have many applications. So thank you.